Okay, so good morning, everyone. My name is Augusto Vega from IBM T.J. Watson Research Center. Today I will talk about some work that we are conducting in the context of multi-vehicle map fusion or perception using GNU Radio. Specifically, I will present some optimization and acceleration opportunities that we have identified and explored and studied. This is a relatively large project, so let me acknowledge not only our IBM collaborators, but also our university partners, which include Harvard University, Columbia, and the University of Illinois at Urbana-Champaign, plus all the brilliant students, postdocs who are doing amazing work here. Special thanks also to Dr. Tom Rondeau, who is the program manager of the DARPA-sponsored DSOC program, under which we are developing this work. So today I will start talking about let's say an umbrella research topic, something that we call adaptive swarm intelligence, which is, or we hope it will be a novel computation paradigm. Then I will go into more specific. I will present our DARPA-sponsored EPOCH project, which revolves around this adaptive swarm intelligence idea. We have developed under that project an application for connected autonomous cars, and then as a result, I will focus on one specific piece of that application, which is an AO2.11p transceiver using GNU Radio and some performance optimizations and exploration that we have done of that specific piece of the code. So we all know very well that the number of connected devices is growing very fast and will keep growing. Some people say we will have like 80 or 100 billion connected devices in the world in a few years, generating huge amount of data. The way we have evolved so far is very device-centric, putting our attention in making those devices as powerful and capable as possible by making them, putting more, let's say, computation resources on the devices. In the case of the cars, putting more sophisticated sensors on board, etc. We believe that we can exploit, leverage an alternative approach, which is the swarming approach, trying to make those devices to collaborate with each other in order to enable a level of cognition and adaptability to unseen circumstances that can only emerge synergistically from the swarm, but not from individual devices. So that is the ultimate goal of this paradigm. We also believe that swarm intelligence can help devices to learn from each other, to exchange experience, to exchange knowledge, in order to learn over time. And this is probably one of the most important differences compared to traditional swarm intelligence, where devices basically follow simple fixed rules. So that is probably one of the novel parts of this adaptive swarm intelligence paradigm. So this is not just distributed computing. It's beyond that, right? We want these devices to learn from each other, to evolve over time. Why we think adaptive swarm intelligence is going to happen soon? If we look backward, we can remember that in the 90s, a small scale processor fueled by very large scale integration gave rise to mobile computing, right? Then we had pervasive sensing, where virtually every physical device became a source of data. So these two enablers, a small scale processor plus pervasive sensing, gave rise to the IoT revolution. What we have now, or we have very soon, is ultra high bandwidth, low latency connectivity, for example, through cellular 5G, right? And we believe these are the three key ingredients to enable the next big revolution, which we hope will be along the lines of adaptive swarm intelligence. Adaptive swarm intelligence, ASI, has applications in multiple domains, going from network cybersecurity, connected cars, unmanned aerial vehicles, or in general, cyber physical systems. But today I will focus on the case of connected and autonomous vehicles. If we look into how cars are evolving and how automakers are thinking about future connected and autonomous cars, we will see that, again, the approach is mostly car-centric. We are trying to put more sophisticated sensors in the car, lidars, radars, cameras, etc. We are trying to put more powerful computers on board, right? But that car-centric approach, we believe, still has some limitations. This is a very simple example where a car is doing object recognition and properly identifies two cars in front of it, but also identifies a person and a few bicycles, which in reality are just a decal stick on the back of the car in front of it, right? So this is a very simple example of misclassification or false prediction, right? So we believe that if we exploit the interaction between vehicles in something that is usually known as multi-vehicle cooperative sensor fusion or cooperative perception, we can alleviate this kind of problems, right? In other words, if we want to significantly reduce the number of fault predictions, and this is qualitatively, I mean, this is not a quantitative chart, if we follow the car-centric approach, it doesn't matter how much computation power or sensing power we put on the car, we won't be able to reduce that rate of false prediction that significantly compared to a case where we also follow the swarm-based approach. So we are not saying that we have to get rid of the car-centric approach. Of course, I mean, the cars have to be more powerful, of course. But we should also exploit the swarm in between the vehicles. So with that in mind, with that motivation in mind, we started like 1 year ago this DARPA-sponsored EPOX project in which we have developed an application for connected autonomous vehicles. So this project, the EPOX project, is part of the DARPA-sponsored Domain-Specific System on a Chip, or DSOC program, led by Dr. Tom Rondeau. The main goal of the DSOC program actually is to develop heterogeneous hardware, software platforms, chips, to basically meet some metrics of interest, including performance, throughput, and power efficiency for a given application domain of interest. In this context, a domain is larger than an application. Actually, in our project, we talk about a super domain of connected and autonomous cars, which integrates elements from, for example, computer vision, as well as software-defined radio. So the efficient programmability of cognitive heterogeneous systems, which is this EPOX project led by IBM with our university partners, is our proposed solution for the design challenge presented by the DSOC program, basically. It's a very large, relatively large project, so I cannot cover all of it. But basically, what we are trying to do is to take this EPOX reference application from the context of connected autonomous vehicles and create a novel methodology that will allow us to generate the underlying domain-specific SOC to execute such an application domain and meet some performance, throughput, and efficiency metrics. So in this process, we are working to develop an advanced compiler for these kind of scenarios, an advanced OS scheduler for heterogeneous platforms. We are also creating algorithms for ontology discovery, which basically means to analyze the application and detect in a more or less automatic manner what portions of the application are good candidates for hardware acceleration. We are, of course, implemented a novel hardware development methodology that at the beginning will involve FPGA prototyping, but we also plan to tape out this chip. So it's a relatively large project that I cannot cover fully, but today I will focus actually on only one piece, which is this EPOX reference application. So the EPOX reference application, or ERA, as I mentioned before, integrates together elements from computer vision and software-defined radio in a single open source application or workload. So the communication fabric implements a protocol using radio for vehicle-to-vehicle communication, AO2.11p, while the sensing fabric takes care of all the sensing activities, for example, from cameras in the car, as well as generating a representation of the world, of the surrounding world in real time. In this case, we are using two-dimensional occupancy grid maps, where the car is centered in a two-dimensional grid map with information about obstacles around the car. So very, very simple in this initial version. That part, the sensing fabric is mostly implemented using the robot operating system, ROS. So we are integrating together these two worlds, radio and ROS, in the same software platform. So ERA is actually one specific adaptive swarm intelligence use case. Maybe a simple one, but still one specific implementation of the ASI idea. So you are, you're invited to check out the code. It's open source, and eventually reach out to us if you find any interest or any way to contribute to it. So now I will focus on one specific element within the ERA application, which is this vehicle-to-vehicle communication box there. Actually, this is a part that we didn't implement, but we rely on open source implementation of the AO2.11p transceiver implemented in GNU Radio by Dr. Bastian Brues. So this code is available in this link here. So we took that code and we integrated it into our main ERA platform. So of course, as any transceiver, we have a transmitter chain and a receiver chain. So what we initially did is to conduct, let's say, very straightforward performance analysis of that transceiver. And we detected that some blocks, the one in red in the receiver, for example, are the most CPU-intensive ones. And specifically, within those blocks, we identified two functions, which is a function to compute the complex exponent and another function to compute the Viterbi butterfly, which are the most CPU or time-consuming ones within those blocks. So at the beginning, we said, okay, let's focus on these two functions as two possible candidates for performance optimization and hardware acceleration. Another thing that we did, very, very easy stuff here, say, okay, let's try to measure, what is the potential performance benefit that we can get in return if we decide to optimize these two functions. So we took the transceiver, we created a version that works in a loopback mode. Basically, what we inject in the transmitter is fed back into the receiver. And we measured the rate at which the receiver can decode data as a function of the rate at which we inject data into the transmitter, which is this chart here. Ideally, we want the receiver to keep the pace with the transmitter, which is this ideal scaling line here. But what we see in our baseline, which is an ARM Cortex-A53 processor, is that the receiver actually hits like a saturation point, right? At certain, around 400 kilobits per second, right? So we started measuring the same using an ideal version of the Viterbi function. Ideal means that we replace the original function with a function that is completely empty and just return a pre-computed value. This is only to know what would be like the potential benefits for that kind of optimization. Even if the computation is not semantically correct, let's say. We did the same with the complex exponent, which actually provides higher benefits, of course, because this is the most time-consuming of the two functions. And then we have measured the same, having both ideal versions of Viterbi and complex exponent, which provide a little bit more benefit. So this is basically our upper bounds in terms of how much performance improvement we can get. Then we focus on one of these two functions, the complex exponent one, and we executed it across different platforms. We started with a baseline ARM Cortex-A53 CPU, and we measured that each invocation of that function takes around 37 CPU cycles. And then we created our own hardware accelerator on an FPGA, right? This is the formula to compute the complex exponent. So what we created was a dual data path pipeline where one branch computes the exponent and the other branch computes the cosine and the sine, and we multiply them together at the end to generate the final complex exponent result. And with this relatively straightforward implementation, we managed to reduce the computation time from 37 to around 6 or 7 cycles per invocation, although most of the time here is basically memory copy overhead, which is not nice. Then we said, okay, let's do something even simpler. Let's create a vectorized version of that function using the ARM SIMD extension, the Neon extension. And that was even better than our hardware accelerator. We basically measure around 5 CPU cycles per invocation. But that was because our hardware accelerator was pretty, let's say, conservative. So we say, okay, let's think about extra optimizations for our hardware accelerator. And this is actually just a projection. We don't have this last part already implemented and tested, but we think that we can increase the frequency significantly. We can have 4 copies of this pipeline instead of only 1, and more importantly, we should be able to completely get rid of that memory copy overhead. How do we do that? So in terms of frequency scaling, it's easy. I mean, we crank up frequency from, in this case, 100 to 300 megahertz, but we have to be very careful. We have to, basically take into account that, for example, the AXI interfaces in the FPGA platform are stable at that frequency, something that we believe happens. Then having multiple copies of the accelerator is easy, but we need enough FPGA real estate, and we need enough available AXI interfaces. So we need a larger FPGA for that. And the most important optimization, which is getting rid of this memory copy overhead, this is a trickier one. What happens today is that, the way the new radio buffers are implemented forces us to basically have this extra memory copy step here within the physical address space, right? I mean, the buffer is mapped from virtual to this chunk of physical memory. And since this mapping is changing all the time because the buffers are dynamic, we need to all the time copy data from here to there, which is from where the FPGA accelerator reads and writes data. If we could fix GNU Radio to have a static mapping of the buffers from virtual to physical memory, then we don't need that extra copy step, and we would completely get rid of that memory copy overhead with a potential improvement of 33 times in terms of performance, right? So these 3 optimizations are not yet in place, but we believe the 3 of them are doable, are feasible. So this is our next step in optimizing our hardware accelerator. What I showed before was by taking the transceiver and creating a standalone version of it that works in loopback mode on an ARM processor without over-the-air communication. So we said, okay, how do we know that what we have been measuring is correct? So let's try to replicate the same scenario, but in a more realistic scenario with over-the-air communication. So we had, in this case, measurements in a setup with 2 machines, one transmitting, the other one receiving over the air with the proper USRP devices. So we measure different kind of scenarios, for example, 2 coding schemes, BPSK and 16QAM. The chart on the top basically is showing the CPU time for the different blocks in the transmitter for the 2 coding schemes, while the chart in the bottom is measuring the same, the time consumed by the different blocks in the receiver for the 2 schemes, plus the noise case, where we are actually not transmitting anything, but still there are some blocks in the receiver which are doing work, right? For example, the ones for synchronization, right? So the message here is that what we observe here matches what we observe in the other scenario where we were not doing actually over-the-air communication. So this is more like a sanity check for us, right? So to summarize, basically what I presented today in a very generic way is a novel computation paradigm that we call adaptive swarm intelligence that we believe will be like the next revolution now that we have, or we will have, ultra high bandwidth connectivity, which is a key element in swarming. Connectivity is the king. Then I focus on one specific use case, this idea of cooperative sensor fusion, which is the application that we took within our DARPA-sponsored EPOCS project. This application basically integrates together elements of computer vision for local sensing plus vehicle-to-vehicle communications using software-defined radio. As I said, I mean, in ASI, communication is key, it's really important, it's crucial. So we started focusing on the vehicle-to-vehicle communication part and analyzing the performance of that piece of the code. And this is what I presented today, actually, this detailed characterization and some potential optimization and acceleration opportunities for these 2 functions that are the most critical ones. But in general, and I think this is, the most important message I want you to take, I mean, we are working on this EPOCS reference application, ERA, something that we started like maybe 1 year ago. And we want to create, out of ERA, like a benchmark platform for cooperative mobility, which integrates together perception and communication capabilities in the same software platform. This is, let's say, pretty unique. Most of the time when we talk about connected autonomous vehicles, either we find a benchmark suite for computer vision and onboard planning and control, or we have separately other benchmark for vehicle-to-vehicle communications. I think we need to create a single unified platform for that and open it for collaborative development. So please feel free to reach out to me, to us, if you see that, I mean, this is of interest to your work and you may have any way to collaborate or contribute to this idea. This is a longer, maybe very long term goal for ERA. So that's it. Thank you for your time. I don't know, I will appreciate if you have any questions.
Time for questions. I just need some raised hands.
So can you are looking at how to expand beyond just the software a radio, but radar, so you can actually use convenient energy and then do a passive receiver, so you can actually have a moving picture of where you're going, right? So you can fuse that together. Did that make any sense?
So the question is if we have focus also on exchanging other type of information in addition to conventional radar. We are considering other, I mean, actually that is a question that we have open in this project. What should we exchange between vehicles, or in general between devices in a swarm, to make this problem of interest? Right now, what we are exchanging is something relatively simple. We create these two-dimensional occupancy grid maps, we compress them together, and we exchange across nearby vehicles. So when a vehicle generates its own map and receives other maps, fuse them together to generate a version that hopefully is, let's say, more precise, has fewer false positives or false negatives. Right. But in the original ASI paradigm, we want to also exchange knowledge. I mean, if a car learns something over time, how do we exchange that knowledge between vehicles? We believe that we need a common knowledge representation mechanism to do that, because we are talking about maybe...
That would be the ontology?
No. Ontology is a piece of the methodology that takes an application, whatever, I mean, arbitrary application, in this case, the ERA application, and automatically identifies portions in the application, functions, or even processes, which are probably the most time-consuming ones, or the most critical ones for hardware acceleration. So this methodology, the ontology will tell us this part of ERA should be accelerated, for example, in hardware, and with this. So
that's ontology.
That is the ontology analysis discovery part of the methodology. Okay. Yes.
Any other questions? I'm going to ask one question that is actually not about your slides. Industrial/commercial research centers don't always gravitate towards open source software. In some cases, even shy away from it. And yet, you're going like even further. You're also putting it out on GitHub. So what was the thought process, mentality behind that?
Well, I can talk about IBM specifically. IBM is actually trying to go open source, open in general, because we are also going open hardware, right? More recently, right? You know, we have the open power platform too, right? So right now it's part of IBM culture to go open source. We believe in collaboration. We strongly believe in collaboration. And we learn over time, probably over many years, and maybe sometimes with some pain in that process, that closing things doesn't help anybody, neither their own company. So this is why IBM believes in doing that, and this is why we are putting everything in GitHub. Yeah, I don't know if that answered to.
Oh, you will certainly not find any disagreement from myself or many people here. All right, one more applause for our speaker.
Thank you.